Welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video, we should be able to finish up our implementation of parsing an expression to a tree. So the code that we have so far, in the last video, we moved what had been our evaluate up to a parse function, and it's supposed to parse out to our node type, and we created our node hierarchy where we have a trait for a node that has an apply method in it, and then our number node, variable node, and binary op node. Now while I'm here, I should go ahead and make all of these override. While that is optional, when the method that you are overriding is abstract, as is the case for the apply here, that's a good habit to get into, because if we were to implement this here, it would cause problems, and also by putting override here, we ensure better error checking. Okay, so we still have a bunch of red marks in our code though, and that's because this says it's going to return a node, and right now it doesn't. So we need to look at each of the different places where this is stopping, and decide how we're going to change things. So if we start with the parentheses, well, then we want to call, this is now called parse to tree, and it takes just that substring because parse to tree just takes one argument. The way we had been detecting variables was using checking to see if they were in the map. Of course, in this case we don't have a map, and the reason we don't have a map is because the map only needs to be passed in when we actually evaluate the expression, not when we're just parsing it. When we're just parsing it, we should be able to find our variable nodes. So I'm going to flip things around a little bit and do what I had mentioned was the other possibility. So I'm going to put in a try block here where I catch and have a case for an exception of type number format exception. Now I can't return expr to double. Instead, I'm supposed to return a new number node that is wrapped around expr to double, and our number node is in the companion object, so I have to use the full name for that. And this is now happy because we're creating a node, and the number node is supposed to wrap around a number. If it throws an exception, we're going to assume this is not a number node. Instead, this is going to be a variable node. And for the variable node, we're supposed to pass in just the name, and that can be what we have for our expression here. Okay, what about these cases? Well, in these cases, we're supposed to create a binary op node. So we know that each of these is going to have new expression parser dot binary op node, and I can copy that and paste. Now the binary op node takes three arguments: an operator, a left, and a right. The left and the right we kind of have in here, except it's no longer called eval, it's parse to tree. And parse to tree only takes a single argument. Similarly, so whereas we had plus, minus, multiply, divide, now this is just another argument. Obviously, somewhere the information about these being addition, subtraction, multiplication, division have to be present. So that's the, okay. And let's make sure this is not enough arguments. That's the error that I wanted, because our binary op node, in addition to left and right, needs to take an operator that is a function that takes two doubles and returns a double. In the case of plus, we can write it simply as underscore plus underscore. So something plus something is our short function literal for minus, underscore minus, underscore, underscore times, underscore, and underscore divide by underscore. And sure enough, now all of the code up here for parse the tree is happy. The last thing that we need is we need to make it so that we can actually test this. So we can make an expression by making a new expression parser, and we can pass it this string. Okay. Now what I want to print is evaluating the expression. And the way that we will do that is we need to put an apply method in our expression that we pass a map to, a map that has all the variables that we want defined. So I'll put that inside of here, def apply. It's going to take vars, which is a map of string to double. This returns a double. And the way we write apply is fairly simple. Root applied to vars. That's all we need to do. And now this code is happy, and we can run it, and because x is 2, this should give us back the value of 22, which we had last time we ran it. The advantage of doing it this way is that then I could call this again with a 3, and note that when I do this, it's not actually reprocessing the string. So this time should be 12 plus 15 for a value of 27. And sure enough, we get 22 and 27. So we have the correct values coming out of this. We could call this many, many times, and it would be significantly faster because the apply is just doing this. Now, of course, when we do this, it's cascading down through. Calling the apply on root is doing this, which is calling apply on the left and right side. But it turns out that calling these function literals is much, much faster than actually processing through the string. So by doing it this way, we parse the string once, we build the tree, and then we get fast evaluation from that. So hopefully this has shown you another interesting use of trees. Also some nice use of recursion in here. There's also one other interesting thing that this kind of has. This has a almost, I don't want to call it a pseudo recursion, where apply methods, so the apply method in the binary op node actually calls apply twice. The reason why I refer to it as pseudo recursion though is because it doesn't always call this version of apply. It often calls the versions that are in other subtypes. And so that's a slight twist on the recursion that we've seen so far. That's it for this video, and we'll come back in the next video and look at how we can make an immutable binary search tree.